You are told that the velocity profile inside a pipe is equal to the equation provided in below. The velocity u is defined by a parabolic profile. So that equation that you see there is just defining the parabolic profile. It's the velocity at any given point, this guy here, over a constant velocity, which can be, for instance, velocity in the center, equals 1 minus a radius at any given point, minus the radius of the constant radius would be the radius of the pipe or the duct or anything like that. The temperature is defined by a simple form of the heat equation written in cylindrical coordinates. So this equation here, this is the energy balance equation. This, you can find this on the class that's been shown to you before. The way that this shows up is when you have a certain, if you have a fully developed flow, and I think there's another thing we need to use to approximate to this. But what the unknowns here are 1 over velocity at any given point, the radius at any given point, times the derivative of r times the rate of how temperature is changing with r. So if you guys recall, see if you paste this, yes I can. Just grabbing the drawing from before. If you guys remember that we were talking about how there's a velocity profile, just like that there's a temperature profile, right? We would expect a temperature profile because obviously the molecules that are closest to the wall will be at a higher temperature than the molecules in the center, right? So that guy there is telling us how the temperature is varying as we go along the radius, right? So if I increase my radius, how is my temperature changing? But not only that, we're also amplifying that effect, that rate, by the radius. So the greater the radius, the bigger that effect is, the smaller the radius, the smaller the effect. And we're seeing how that whole thing, the amplified change in temperature in respect to radius, is varying with radius. So it's the rate of the rate. That has to be equal to 1 over diffusivity, molecular diffusivity, times how my temperature is varying with x. So remember that x is on this direction here. Let's change this. Let's change this. Instead of having L, let's have x and then put an arrow, right? So x is, as opposed to r, is on the horizontal direction, right? And as opposed to r, what we're asking is, okay, how's the temperature here different from the temperature here, from the temperature here, from the temperature here, from the temperature here? How is that changing as I go down x, as my x increases? Okay, well, if the guy is fully developed, then we would not expect any changes in the velocity, right, on one direction. So for a lot of cases, especially if it's laminar flow, then our temperature should also be constant on the same, as we're going down x, we shouldn't see the difference in temperature. So derive an expression for temperature profile inside the pipe. You should get the equation as shown below, so you already have the endpoint, like I said. You may assume dt dx to be constant, like I just mentioned. So we wouldn't find any change in temperature as we're going down the x direction, and we can call that theta. So that's the theta over here. And we have a velocity profile. Remember, they said they were going to give us the velocity, the equation below. So the equation provided below, that's the equation provided below, just this one here. Okay, what is this one telling us? It's telling us that the velocity is a function of the radius cubed. Okay, so we're grabbing these equations and we'll solve and try to find the equation given. Okay, there's more than one way to do this. I'll show you the one that I did, but you're welcome to do your own. Okay, I'll just rewrite the equation. So r cubed over 4. So that is one equation that was given. And I'll just rewrite the other one too, which is saying that 1 over r velocity derivative in respect to r of r times how temperature is changing with r has to be equal to 1 over diffusivity, how the temperature is changing with x. All right, first thing I'm going to do is I'm going to send this fellow multiplying to the other side. So this will just be u naught, and I wonder if I want to, yeah, I'll just do this u naught times r cubed over 4. All right, the next thing I'm going to do is, as you can probably tell, I'm going to sub in where I have u, I'm going to sub in that equation. But before I do that, I'll first send these two guys here multiplying that side there, and I'll call this fella theta like they told us to. Oops, there's missing a dt. Okay, so this will become derivative in respect to r of r dt dr equals radius times velocity divided by my diffusivity. Oops, and this is theta now. Okay, so now what I'll do is I'll sub in this guy into here. So derivative in respect to r derivative dr equals r over that. And where I have u, I'll have now instead, I'll have u naught minus u naught r cubed over 4. It's checking over 4. That's it. Brilliant. Now what I'll do is I'll remove, I know I've put that before, but I just did it in small steps. So I remove my u naught from inside this parenthesis, and I will multiply my radius. R dt dr equals theta divided by diffusivity, u naught, so this guy came out of the parenthesis, and inside my parenthesis now I have r minus r cubed divided by 4. Okay, so the next step, and I'll put a little star here because we're going to end up using this in the future. This step here. The next step is I'll send the. I'm going to send this guy multiplying to the other side. So I have the derivative r dt dr equals theta u naught diffusivity r minus r4 over 4 dr. Okay, the reason why I did that so that it can integrate. And if I integrate on both sides, what I'll have is I'll be able to eliminate this derivative here, and then on the right side I'll have to integrate in respect to r everything, right? So let's do that. I'm integrating here. I'm not defining my integrals, so I'll have constants by the end of it. On the left-hand side, it's pretty easy because we just literally just eliminate the derivative. On the left-hand side, it's not hard, right? Because we know if I'm integrating this, so if I'm doing r dr, that's just going to be r squared over 2 plus a constant. And if I'm integrating this guy, that will be, so integration of this dr, that would just be r to the 5th over 5 plus a constant. Yeah, so simple integrations there on both sides, on both the two sums. So my constants stay as constants. You don't care about the integration. One of them, my radius will be r2 over 2. The other one will be r5 over 5, and then we have a 4 there, so 5 times 4, that's 20. And we're going to have two constants, but I can sum them up because they're constants. So if I sum two constants that I don't know, I'm going to get a third constant that I don't know, so I can just have that one there. Okay, so I'm going to have to eliminate these constants eventually, and that's why now I want to put that star there, so I can remember where I'm going to do that. Okay, so what do we do next? I'm going to divide everything by r, so I'm going to say as long as my r is different than 0, I can divide everything by r, so I can eliminate the r over here. So on the left-hand side, I'll just be left with dt, come on, dt dr, and on the right-hand side, I'll have theta u naught diffusivity r2 over 2 minus r5 over 20. All of this multiplied by I'm dividing by r, right? So I can downgrade these guys. So this is going to be r. This will be r4. But over here, I'm also going to have r, right? So I'm going to have r. That. Okay, at this point, we can integrate one more time. So I can send this guy this time multiplying to the other side. So I have dt on one side, and the other side I have theta u naught diffusivity r over 2 minus r4 over 20 plus dr plus c1 over r dr. Once again, I can integrate on both sides. Note that on the left-hand side, I'll just have temperature plus a constant, or minus plus a constant that I don't know. On the right-hand side, I also have constants, so I can sum up constants and just have one constant for every single one of them. So I'm taking the integral on the left-hand side and on the right-hand side at the same time, and then obviously we'll have an additional integral over here. So it ends up being 3 integrals. On the left-hand side, it's pretty easy. It's just the temperature at any given point. On the right-hand side, what's constant remains constant. Then this guy, same thing, right? R squared over 2. So I have R squared over 2, and there's a 2 there, so there's going to be a 4. And we also have R4. We're going to go elevate that to the 5th. So it's going to be minus R 5th. And then divided by 20 times 5, that's going to be 100. And over here, if you guys recall, that or what we're really doing is just we're integrating. So we're integrating this, right? The constant can come out with the derivatives, and this is just a natural log. So it'll be C1 times the natural log of R. And obviously we have a second constant because all these 3 integrals, they render a different constant that I'm summing all up to have a single one. Okay, so at this point here, we've pretty much finished the, let's say, the generic part of this problem, right? If you look, let's compare with our end goal. Let me grab, actually, let's do this. Let's use technology. Copy. Let's see how similar or how far we are from the end goal. So note that theta times u naught over the diffusivity we already have, it's all good. Inside the parentheses as well, we already have what we're looking for. What we don't have is this TC, which refers to T center, temperature at the center. And we don't have these constants here, so we're going to have to transform that. Just by analyzing, if you guys are very cheeky, just by analyzing, you can see that C2 will be TC and C1 will be 0, right? Just by analyzing our end goal. But obviously, let's pretend we don't know our end goal. Let's see how this comes to be. So for us to eliminate the constants, we need boundary conditions, right? So I wonder if I still have the drawing. I do. Grab this drawing. Let me eliminate these guys so that they don't confuse anyone. Let me grab this drawing, place it on the bottom there. And let me go ahead and ask you guys to see if you can think of any boundary conditions that we can use. I'll pause the video and then you guys think of it. Okay, so those are the boundary conditions you guys said. So one is that when my R is 0, then my temperature is the temperature at the center. The other one is when my radius is 0, the way that my temperature does not change with the radius, because my temperature on the center won't change with the x. Okay, so let's apply these 2 boundary conditions. But note that I can apply these at any given point, and I'm going to be cheeky and apply, that's why I put the star there, apply one of the boundary conditions over here, because then I can eliminate one constant and only have to deal with the second one afterwards. Okay, so I'll apply this boundary condition here. When my radius is 0, my dT/dr is 0. So 0 times 0, u naught, diffusivity, 0 minus 0, plus C1. So therefore, T1 equals 0, like we would expect, like we expected, right? By seeing the final answer. So let's now grab this one here. Let's grab this one here, and let's continue now that we know, now that we could eliminate one of the C. So this, let's put this here, this goes to 0. Okay, next boundary conditions, let's use the one that James mentioned. When my radius is 0, the temperature is the temperature of the center, so Tc. Again, just nomenclature, really not really saying much. But we can apply that condition to that we can have a situation, so we can eliminate T2, right? Because, let's see, my T has to be Tc, so Tc equals theta U naught diffusivity. My radius is 0 minus 0 plus C. So just like that, everything went away, and we're left with a very simple conclusion, which is that T at the center equals C2. Okay, so now if we apply our new knowledge to the general form of the equation, we found out that this guy is 0, and therefore this whole term goes to 0, and that this guy here is Tc. So that means that T equals theta U naught diffusivity R2 4 R5 over 100 plus Tc, and therefore T minus Tc equals theta U naught diffusivity times R2 over 4 minus R5 over 100. And this should be exactly the same as the one that we had to start with. So let's make sure of that. Grab this, and we can go all the way up there and check. So T minus Tc equals 1 over diffusivity, theta times U naught. That multiplies the parentheses inside, R squared over 4 minus R to the 5 over 100. Great, good job, you got it. All right, any questions?